So our next application of derivatives is looking at extreme values. If we look at any continuous function that is on a closed interval, so if we look at absolutely anything and then we close off its interval, so let's say we're looking at the region from A to B. This will be our A value, this will be our B value. It's a closed interval, it's continuous in this area, keeps going beyond. We can find a minimum and a maximum value throughout this function. Now in this particular case, the maximum value would be the inflection point, the point where it changes direction on this portion of the curve, and the minimum point would be the lowest point. Now if we had actually changed our function so that it was on an interval where B was actually, say, over here, we could actually have a different minimum point. It could be either of these 2 points depending on which one's the lowest one. So let's say that's the lowest one. So this could be our minimum, this could be our maximum. It doesn't always have to occur at an inflection point, it could be on the edge of the interval. Because it's a closed interval, they exist at those points. So again, if we had any function that went up and down, over here, up and around, etc., if we consider a closed interval on it, let's say we look at this little section here, there exists a minimum and a maximum in that interval. The minimum value is the lowest possible point. In this case, it is the inflection point where it changes direction. And the highest point happens to be right here on the edge of the interval, so at the A value, whatever that might be. Now some of the terms that you've probably seen before are local minimums and maximums, the absolute min and maxes. If we look at an open interval, so the entire function, we can look at a graph and see that we have a minimum here, maximum here, minimum here. This one here, because the function is opening up completely upward, they'll never ever go lower, this is referred to as an absolute minimum. This guy here and this guy here, this one is referred to as a local max and a local min. In the case of this graph here, let's say it's a cubic, again, we do have 2 inflection points where it changes directions. This one here will be a local max, and this will be a local min. There is no absolute min on an open interval because it continues on to negative infinity and up to positive infinity. Although, if we actually restrict this and we make it on an interval, so on the interval say AB, let's just choose any point A, and let's choose this one here, and B. Inside of here now, we now have a local max, which in this overall interval is also our absolute max on the interval AB, and we also have here a local minimum, which was an absolute minimum of the entire function, but also on the area of AB, or the interval of AB, it is also an absolute minimum. Same idea here. If we were to choose, let's say, here to here, A to B. Now if we're looking only on the interval, we have a local minimum, which becomes an absolute minimum for the interval AB, and we actually have a point here which is referred to now as our absolute maximum because it's on the interval AB and it's the maximum point within this region, even though we have a local max outside of the region. Now the critical points and the points on the AB intervals are referred to as our critical aspects. If we're looking at critical points, basically we're looking for where our derivative is going to be 0. Derivative 0, derivative 0. These will give us our inflection points. So wherever we have a derivative at that point, let's call it C, D, and E, in this particular case, the derivative at C is equal to 0, the derivative at D is equal to 0, and the derivative at e is equal to 0. Those 3 points are critical points. They have a horizontal tangent, which means the slope is 0, which shows that it's gone from one direction to the other because it's changed its direction. There are other cases where we do have critical points, and it's where the functions are not differentiable. So if f prime of, let's just say, c, another point, it does not exist, then it's also a local min or max, a critical point. Now, if you need a reference, remember with our absolute values, that would be our critical point here where it changes directions, but there is no actual derivative at that point because the slopes don't ever approach the same value. Now, an important theorem is Rolle's theorem. It basically follows from what we've been talking from, but it's just a formalization of it. If we have any function that is continuous between a and b, so let's say a is here, b is here, and it is continuous. So we're only going to look at this region here to here. And let's say we draw in something that does that. Okay? So it's continuous in this interval. And it's also differentiable. So it is differentiable. We don't have anything where the limits are not approaching the same value. So if we have our a and b equivalent, so let's draw this slightly different. So if we draw this differently, we can actually draw in a function that's going to have the same y values. So if we actually look at this, it's now saying between f of a and f of b, there exists a value between a and b, c, such that the derivative is going to have to equal to 0. And if we look at our graph, yes, there is a point here where our tangent is going to be 0, or slope of our tangent, I should say. So Rolle's theorem basically says that if you find 2 points, a and b, that are your interval on a differentiable continuous function, then there exists a point c within this region where the slope is going to be 0. So now let's take a look at an example where we have to find the minimum and the maximum on a particular interval. So we know that min and maxes are going to either occur at critical points or on the edges of the intervals, because that's where they'll be touching. They'll be the highest possible points. So if we look at finding the derivative of the function, we would get this. Now, we ultimately want to find out where the critical points are. Does it equal 0 anywhere? So if we substitute 0 in for y prime, for the derivative, and we factor this, we can find that t is going to have to equal 0 or -1. Now we're looking at the interval from 1 to 2. So that means our inflection points, or points where it changes direction, occur at t equals 0 and -1, which is not on our particular interval. So what we need to do is figure out the values at 1 and 2, because those will be the points where it touches on the edges of the intervals. So if we plug in 1 cubed plus 3 times 1 squared, you're going to get 2 plus 3, so you're going to get 5. We're also going to have, so we'll call that point 1. y2, we're going to have 2 times 2 cubed plus 3 times 2 squared. That's going to be 16, plus that's going to be 4 times that, so 12. So you're going to have these two values. That means at the edges of the intervals at -1, or sorry, at +1, you're going to have a y value of 5, and at +2, you're going to get a y value of 28. So this one will be your minimum value in that interval. This one will be your maximum value in that interval. Now, if our interval was not between 1 and 2, let's say our interval was between, let's say, -1 and 1. Now we have a critical point that occurs in that interval. Actually, we have 2 of them. So then we'd have 0 and -1 as both our 2 values. Those would be our inflection points. So we'd want to plug in then, let's plug in our -1 because we haven't done that one yet. that would become -1, so -2, plus that would be +1, so plus 3, so y3 is going to equal 1. And then our other point of interest is at 0. 2 times 0 plus 3 times 0. So now in this case here, we've actually found that y3 is equal to 1, y4 is equal to 0, but we do have to consider the entire interval. So if you look at just a number line, there's -1, there's 0, there's 1. -1, we get a y value of 1, 0, we get a value of 0, and 1, we've already calculated that, we get a value of 5. So this is a critical point because we did find it that is a point where it changes direction. This one happens to be our minimum. Whereas these two, this is a critical point and this is the edge of our interval. When we compare the two of them, this one is our higher value, so it's our maximum.